Before starting my talk, I would like to express my sincere thanks to Corinne Taylor, who kindly invited me to have this wonderful opportunity to share my research and concerns with you. Then today's topics is, in some sense, not familiar in this course of the lecture, but I think one of the good application of the complex system for the practical or policy-related issues, I think. What we today I'd like to talk is the economic impact assessment of disruptions of production capital and critical infrastructure. But this is related kind of the economic impact analysis which caused by disaster. Disaster definitely brings about many different types of losses. One is definitely human lives. The other one is property losses. But the property losses, human life losses, these are the kind of the losses in some sense stock in economic term. But why we want to work hardly for the disaster risk management and disaster risk reduction is also we want to reduce flow-term losses. Flow-term losses is occurred when after disaster if we cannot treat disaster properly. But to treat disaster properly, we need to have some preparation in advance. So I'd like, of course, this is not very much directly related to the such a preparation or the other disaster risk management countermeasures discussions. But I want to tell you that how the each part of the system relates to the such a big consequences of disaster. This is a definition of critical infrastructure, which was defined by my former colleague Charles Corson, and he said that the kind of these are those services requested for the function by any groups or organization from village to megacities of society. Without these services, operations or society cannot exist. This is his definition. Of course, there are many different types of definitions. But I think all of you can agree that the water, wastewater treatment systems, transportations, power, energy, or communication, if these infrastructure cannot provided, then we can easy to face with severe difficulty. And then the larger the community, like think megacity, the more critical is the infrastructure. Without water, transportation, power, and a large city must be abandoned within days. We cannot imagine no electricity situation for a month or so. Maybe many things, many subsequent problems may took place. So even after disaster, electricity supply recovery is one of the most urgent tasks for the public authorities. Sorry. Then these industries also affected its production capacity due to the malfunction of critical infrastructures. Cascading effect propagates its impact to the economy through interdependencies of economic activities. For instance, for example, some supply chain questions. One example I bring for you today. This is kind of the problems occurred after the East Japan Great Earthquake, which took place March 11th of 2011. That time, one big company in Japan was affected for its production, but which was making microcomputer chips and for automobile. That is, in some sense, such a kind of semiconductor factory had a kind of the several layers within the big, let's say, buildings, and then that reduced the kind of the they have lots of different, let's say, processes within that line. So they need to have a very efficient 3D, let's say, allocation of the, let's say, production facility. But that definitely means that not easy to keep precision after the big earthquake. You understand? Many facilities can move inside of the building and then turn over, and then maybe let's say, had some, let's say, kind of, they would say, stoppage of the process that causes, let's say, big, let's say, delay or problems for the recovery. Actually, it takes 3 months to partially recover for that, let's say, production line. Of course, within 3 months, the many, let's say, workers, engineers from automobile factory come to help them. Then they have, let's say, recovered sooner than expected. 3 months is faster. Their original expectation is 6 months. But while let's say, waiting that recovery, it happens that, let's say, automobile production in Japan, 50% drop for 2 months. How about the 3rd month? Definitely, they have, let's say, found the kind of alternative sources of the, let's say, supply of microcomputer chips. Definitely, from this, let's say, example, we can also find that critical infrastructure is not only, okay, of course, critical infrastructure, definitely, lifelines or other, let's say, infrastructures, but also the critical parts and materials matters. So this production line is one of the most, one of the key for the, let's say, a contemporary production of the automobile. It means that these parts or materials are low substitutable goods or services. Low substitutable, that is an economic term. But if we can easy to find alternative parts, alternative sources, then it is called high substitutable. This good is high substitutable. But if it is difficult for us to find, if it is difficult for us to find the alternative ones, that is called low substitutable ones. Actually, this case, this is the only company which produces for specific microcomputer chip. That is a problem for this case study. Then, from now, I would like to talk on how to measure such a, say, economic impact of this disruption of critical infrastructures first. Maybe to do that, we need to have a kind of the tools to express the magnitude of disruptions. I'm sorry, I didn't put the years for this. Stephanie Chan or Adam Rhodes, they are both working in North America, Canada, or United States. They developed these types of formal presentation for the resiliency factors. Resiliency factors are the kinds of the mathematical expression for remaining maybe capacity or amount of production under the system disruption. It means 0 means ordinary state, 1 means say the after disaster state. And then this F is a production function. U is a utility or maybe lifelines or critical infrastructures conditions. X is input. So if inputs is this amount, then if there was the lifelines or critical infrastructures is in the I say ordinary functions functionality, then the sum, maybe ordinary production level, can be determined by this function. But if we have lose some function of the critical infrastructures, like if please assume the situation like electricity is not provided, then this summarizes the no electricity situation, how much they can produce with the given product amount of the other resources. Of course, originally they did a kind of the survey for the specialist in the specialist board to determine this factor in the United States. That was very long before. The first one is ATC 13. That was maybe early 80s, late in 80s. Then, but unfortunately, that number is only available in the world that time. So every risk assess economic analyst want to use that. But unfortunately, that depends on the country. Production, features may affect that. So we decided to have some survey in Japan. And then today's discussion based on this survey. And then we got this in Japanese, questionnaire surveys in Japan. But as maybe you can imagine that the E stands for electricity, W stands for water, G stands for gas. Okay. Then this means only electricity is malfunctioned. Then how much was the production? How much production capacity is remaining at this sector? This is written here. The combination is also written here, right? But this one is the first survey, which written in the 2004 paper. Unfortunately, this is Japanese, but the English version is published 2007 in Earthquake Spectra. Then anyhow, you can see that these numbers in the later if you have some interest. Then anyhow, the electricity is one of the key for the production, but for the water, that depends on the sectors. Gas in Japanese context, not very significant, but for some let's say, specific, except for some specific sectors. After obtaining this, we should, let's say, reflect this to the kind of the economic model. To do that, again, economic models representation, which is called the production function. Production function is the transformation function from input to output. Very simple. Input is intermediate goods, and also for this case, gas, water, and power, electric power. If this is a kind of the structured production function, hierarchical we say, then if these are, let's say, getting lower and lower position, it means these are low substitutable. Of course, we can put a kind of the contribution factor in the for each, let's say, input. Then we can successfully, let's say, model for this case. For different sector has different values of the, let's say, substitution level, substitution elasticity of substitution parameter. Then this can be also combined with the kind of the disruption question related to the transportation systems. Transportation systems disruption, in what way we can represent is we can simply model for the economic model for different areas, and that can be connected by transportation networks. That is called spatial computable general equilibrium model, or sometimes a spatial applied. Spatial applied, it is not safe. Sometimes this computable general equilibrium is referred as applied general equilibrium model, but for the which has some dimension of space, that is called spatial computable general equilibrium model, SCGE we call. Then this is a very simple idea. These each region they have a household, many firms. Firms produce the products, and that is contribute for the intermediate inputs for the other firms. Definitely, a household can provide labor and capital, and a firm provide commodity. For each, I would say, goods or services, we have let's say, market in a different region, and then these goods and services can be let's say, transferred from the other region through highway networks, and also the passengers. This is maybe for the business trip, like that. Then if we, let's say, discuss for the details of the model like this, this is intermediate goods, and then that can be combined with the Leontief technology I will show you later, and then a Cobb-Douglas function to, let's say, combine the labor and capital and business trips. And this is a mathematical expression. This is called the Leontief function. This is basically low substitution, low substitutability is expressed. And then this is Cobb-Douglas function. Also, this can be a little bit flexible form. But anyhow, we can have the kind of in the Cobb-Douglas form, basically the cost expense ratio for each factor is fixed. So it is, in some sense, easier to model to let's say relate the existing statistics. And then this one is for the business trip model, and then this is again a Cobb-Douglas form. We can, let's say, get the data from the business trip surveys. And also for the commodity transport, we can let's say we should assume something, but like kinds of the let's say typical assumption is the commodity transported by the shortest routes, or maybe equilibrium assumption. In equilibrium, routes which have a same traffic takes same time. So it means the even the transportation or network, if it is disrupted, then that the time between origin and destination will be different, will be increased. In that situation, we can estimate the shortest time between two origin and destination, or maybe we can estimate the equilibrium time between these two, let's say, area. Then we can use that time for that to be it's reflected for the commodity transportation equilibrium. Next one. This is one of the key, let's say, part to reflect such a disruption. And then this is a kind of in some sense, an entropy type, let's say, a location model behind. But this part, is contributing to measure the let's say, a difference of the transportation cost. It means relate to the transportation time. For household, we can definitely introduce a kind of the consumption for among different goods. So this is basically represented like this. This is a this is coefficient. This is the kind of the consumption of goods. Then the utility is maximized, but given the, let's say, budget constraint. Of course, this part relates to the income. That is also related to the wage. So labor market also affects to this. So we have lots of parameters in this model, and then before this, we assume long-run equilibrium. That means all the, I would say, market is cleared. Then the price is, let's say, in the condition of equilibrium. Then the equilibrium after disaster, that case definitely transportation condition will be changed. And also labor and capital condition is changed. Because disaster may affect the reduction of labor or reduction of let's say, the capital distribution. So maybe factory cannot, let's say, operate in a proper manner. So that way, we can model for this. Then we have some case studies. I'm afraid I have not many time to explain detail for the case studies, but this one is called little bit. This line is too low, but actually the expected, let's say, disruption zones of the earthquake, earthquake zones are like this, which is coming from the around this place to this place, covering these areas. Then one of the most, let's say, awful scenario is now called the Nankai Trough earthquake, which includes from this part to this part, all these areas. It may have a slip when the earthquake take place. Then, but this case, this case just simply assume this part is affected, only small earthquake. Or maybe there was a early warning. We have the kind of a law for the early warning for the Tokai earthquake. That that if we have can successfully predict the occurrence of Tokai earthquake, government issue the kind of the order for the stop of the productions, and also most of the economic activities are stopped while before the earthquake takes place. So that kind of situation, how much, let's say, damage, economic damage to take place. So I want to check that as a scenario. To investigate that, let's say, scenario, we have divided Japan into 14 areas. Because we have 6 regional connected let's say I/O table, input-output table in Japan every 5 years. So based on that, and also the each prefectural government has their own I/O table most of the cases. So we use the combined use to make the 14 area connected I/O table. And based on that, we built up the model for the spatial computable general equilibrium model. And then this is one of the, let's say, intermediate let's say, check for the, let's say, reality of the in terms of the transportation. Trade coefficient is the kind of the share of the goods between two, let's say, share of the goods for that trade for that area. That is, let's say, if that value is right, should be just on the, let's say, simulated value is right, then this is a kind of the surveyed ones that should be on this line. Fortunately, for this case, it is on that line. And then we proceed for the scenario analysis. This is the scenario for this is some of the pickup of the major Japanese let's say highways in this area. And Tokyo, Shizuoka, Nagoya, and Osaka, Kyoto is around here. Not represented as node, unfortunately, but like this. Then next one is for the railroad. And then a scenario, a difference of the scenario is written like this. If the small earthquake took place, maybe disruption is limited around here. But if there was an early warning issued, then this and this should be stopped. This is written in the let's say, government document. And also, for the, let's say, railroad, this is Shinkansen line. This would be stopped. And also, this is another, let's say, railroad in the running in the center part. But this is slow line. But this may be also stopped. So this is the scenario too. Also, for the, let's say, early warning scenario, we stop this 2 routes. Then we check the, let's say, difference. And then the blue one, you can neglect the blue ones. But yellow and red, you should compare. And then one, I mean, the only one that was the major route disrupted, but with some kind of redundancy. So still we have some routes which connect Tokyo to Osaka or Nagoya. That case, it's significantly different between the two. In total, I didn't write any, let's say, numbers. Maybe you cannot imagine, but this is 36 oku yen. That means 80 should be attached to the, let's say, to get Japanese yen. It means 60, so million. 33 million dollars loss can take place if both of the routes are let's say, affected, stopped. But one root, only one root case, that is 1, 1. This is 18. So 18 million dollars loss per day could take place. So the half, we can limit the loss in the half for this case. So this is the value of the redundancy. Another case for the Niigata Chuetsu earthquake, this is a kind of the timeline which is for representing for the recovery of the lifelines. First, from our experience, after earthquake, electricity is the fastest to be recovered because this is a very urgent need. And also, they know very well how to recover it quickly. And the water lines takes some time. Gas lines, more time, from our experience. Maybe water, gas in the different order. Transportation, maybe in between. And production facility itself, completion of the recovery takes long time. But of course, the temporal recovery is within, most of the case, 1 week. Then this is also the network disruption explanation. For Niigata Chuetsu earthquake took place around this place. So this Shinkansen line was stopped. And then Shinkansen line and the highway stopped. And the railway, Shinkansen stopped. Then we have a kind of detour by bus we have at that time. This is another thing I want to introduce for you. This is called functional fragility curve. Based on the survey after the Niigata Chuetsu earthquake, we made also the kind of the survey, questionnaire survey for in the affected firms. So then this is we have asked the following question: your let's say production lines are affected or not? Oh yes, it's no problem. Then they suggest they have regarded in the state 0. Okay, do you ever say production line is completely stopped or not? Then yes, then they are in the state 2. And then also we have another question like how much your production capacity remained. Like they answered 50%, then that is should be written around here. But for this function, we decide to write this curve. We specified the mode of the production. So it means that shutdown, complete shutdown, or at so some effect, like that kind of slight damage, maybe like that. That is written in this like this way. So this line it summarizes the kind of earthquake intensity. Then actually. To represent the intensity, we use the spectral intensity for this. Then we can see that if we, for this case, maybe 55 kind intensity we have, then it is about 20% of the firm stop their production completely. And then, but still, 20%, also another 20% firm is work in the steady manner, the same manner. So we may have this kind of prediction after the earthquake. Using that data, we can estimate the impact of that earthquake. Then this is the transportation impact. These are the lifelines and also the capital deduction. So the difference between these there was a contribution of the for these. So it looks maybe nothing. compared to transportation. But reality, for this case, not very big. But the other cases, it is different. Maybe. Okay, I think you know well for the, let's say, earthquake occurred in Tohoku area in the March 11th. Then that case, we have triple, let's say, subsequent event. One is earthquake itself. Second is tsunami. Third is nuclear power accident. Then to estimate the economic loss, definitely we should think all these three let's say, disasters in the simultaneous manner. Then, oh no, this way. The tsunami affected zone we have estimated by satellite data, and then in this area we assume that production capacity is assumed to be 0, and still close to 0 right now, I think. And then this one is a recovery of the lifeline in the different region and different prefectures. And the electricity recovers relatively quicker, but some area, it's still not recovered. But why this happens, that is basically the difficulty of the, let's say, access to that area. But still, you may see that this is the, let's say, 1 month later period. Only closer to 5% of, let's say, population has suffered for the shortage of electricity. That is basically, let's say, resolved 40 days, I'm sorry, 40 days. And for the case for the water, it took more time. Like this is about 80 days. Still, they have some, say, difficulty for the water. And the gas, it's about also the 40 days. So this case, in the Miyagi, has suffered a lot, but gas recovered relatively quicker. And then again, functional fragility curves are used to estimate loss. And also the lifeline resiliencies. This is I showed by the table. Then this is this recovery time is used for that to estimate the, let's say, impact. Then the facilities. This means for the production facilities recovery. Based on the questionnaire survey again, for this, let's say, particular case, we made 10,000, let's say, questionnaires, and then returned in 20%. So basically, not bad sample we have for this case. Then we can use all the, let's say, things together to estimate the business interruption loss. That is, in what way do that? The way is maybe explained in the following way. Firstly, we use the functional fragility to, say, find the decrease of the production capacity at the beginning. And then we put this, let's say, recovery curves for electricity and water and gas, but this is lifeline resiliency factors levels. So it means then multiply this factor to the existing percentage of the production capacity, then we can get this red curves. This is and also sorry. Then maybe we have this kind of dotted lines. Also, if we use the recovery of the production facility, then that is like this. So we get these area of the losses from this estimation. This is one particular case for the transportation machinery production industry in Fukushima. Then the primary drop of the production capacity is about 27%. But the lifeline disruption causes much significant impact. It is the production capacity down to 5% right after disaster. Then reflecting the recovery of the lifelines, we get this kind of recovery curves. Of course, this is also reflecting the recovery of the production capacity. We using this kind of data, we can successfully replicate the tsunami related loss for the production capacity. This is actually functional fragility, only using functional fragility. Then we can find that in the Miyagi prefecture have a significant reduction of production capacity by tsunami. And also, we include the other, impacts like earthquake, ground motion, and also nuclear power plant, accident. That case, we have also the other prefecture had a severe find a severe impact through these events. In total, around 30% of capacity in these regions are affected. But that region's production capacity compared to the Japanese GDP is about 6%. So 6% by 0.3, it means 1.8% of GDP of production capacity from Japan was lost for this period. Nuclear power plant losses. This is, in some sense, just a kind of the stoppage of the is assumed within 20-kilometer radius. So that is relatively low for this estimation. You can see that just 8% is the maximum intervention for the production capacity in the Fukushima area. This is actual, drop of Japanese production. And then this one is a machine transportation machinery drops. Oh, this number is maybe wrong. Fine, but not easy for you to see. But drop 2 months up lower than 50%. Okay, and the other ones like this one is the paper and the power production worse than that. Then using that data, we can compare our model is accurate or not. Check the validation. The estimated value is written here, and then this one is the index of industrial production, which observed, issued by the government. Then, if our estimation is good enough, then that again should be on the 45-degree line. Please look at red one, red one. Then that is the final result. So that should be on this line. Miyagi, Fukushima, Iwate, these three prefectures most affected prefectures in Japan. So they for their case, this estimation can summarize in a better manner. But the others, like Ibaragi, Tochigi, also they are affected very much, but compared to these three, the slight damage. That case, our estimation for the is too optimistic. This is again for the April. These are basically is relatively good, but these two are overestimated. This is for the May, the 3 months later. Then this is basically Miyagi, Fukushima, Iwate get very much agreed. But the other two is from the model, they should not have any losses, but still they suffering this much loss. So that is why this happened. Because this is not taking account of the supply chain impact. To reflect such supply chain impact, definitely we should use our original model, special computable general equilibrium model, and also a kinds of the special treatment is needed. Then we did some estimation, but for this case, to represent the substitutability question, we use this kind of assumption to combine the goods which produced in the domestic goods and imported goods. This is a kind of the what we call Armington assumption, which is commonly accepted assumption to deal with the trade of non-homogeneous good. Then that case, if these are very much substitutable, this parameter should have a larger value. If it is non-substitutable or low substitutable goods, in that case, this value should be close to 0. This is a kind of the ordinary assumption for the elasticity of substitution parameter. That case, this is a kind of assumed very much of a model case. But if we assume that parameter is at 2.0, relatively easy to be substituted. That case, the loss is limited in the affected area, Tohoku. And then distribution to the other place is very small, because definitely we can find the goods in other place. It is easy. But if we assume the low substitutability, it means the elasticity placed at 0. Then we have very large, let's say, loss in Tohoku, but also the other regions. In total, let's say, loss for this case, 3 times different. Taking a realistic number for the substitution coefficient based on the local survey, then we made a kind of the estimation for this specific case. Then still, we found that the Tohoku area, if we summing up the Tohoku area, then this is in the biggest compared to Kanto. But compared to the let's say primary impact, production capacity loss, and let's say transportation related loss or indirect loss is like this. So for some industry, this induced one is about 30%, but some others 15%. I think it is still something is missing. And then this is transported, again, the index of industrial production in March. Then Tohoku decreased for the 34% in the production. But this is an estimated result from our model. It looks very good, let's say, agreement for Tohoku. But for the other regions, Kanto and Chubu, that also should be smaller, 20% reduction of their production. But from our model, we just find 5% or very small, like 2-3% of the reduction of the production in this area. Why this happened? Maybe we should think of another, let's say, possibility. While this time, the electricity shortage is very significant, that's the reason why the government of Japan asks the factory to reduce the production in 20% in Kanto region, area in Tokyo. So that may be affected for the real production. So I think that is not included, but still, tube areas production is too high. So I think we should be carefully investigate our model as assumption and data, and I'd like to revise this part in the future also. Okay, at the end, maybe I'd like to referring this. Okay, definitely functional fragilities or resiliency factors. If you can use this kind of idea to connect the hazard to economic analysis, then I think we can successfully estimate the economic loss. But still, we have some problems to be solved. One is definitely the precision should be, increased to capture the direct and indirect loss impact as a whole. There are no estimation after the Tohoku earthquake to describe the total loss to Japanese economy, or maybe the world economy. So that kind of research should be done in the future, I think. Second one is that long-term losses are not easy to be estimated, but may be very significant. What I mean by this, if there was a production at the original place can no longer possible, then definitely they should find the other place to work, to start their operation. So it means the location of the firm will be changed afterwards. This is called the long-term loss or long-term impact. This sometimes significantly observed. And that is not observed in a short time, but in the long term. They have, some company will go out from the market also. But there are no, research has been done in this area. And then firms are also not easy to include long-term impact into estimation of benefit of mitigation. This is right. This is also they have short-sighted actually for the mitigation. So from these types of analysis, we found that lots of loss you may think, and you should prepare for that. But of course, I know, but I don't want to do that. But maybe in the UK, you have developed a very nice insurance, and Japan also, but not for the to cover the to not well, let's say, spread in the business right now. So if maybe if we have the better, what they say, penetration ratio for the firms in Japan, it could, let's say, make some contribution for the decision making for all of the mitigation for the firm to increase the, let's say, the percentage of the firm to adopt effective mitigations. Okay, thank you very much. This is that's it for this. This is the end of my lecture. Thank you very much for your attention.